On Friday, we learned how to solve limits graphically. We analyzed the graph and took a look at what was happening as the graph approached from the left and from the right. Today we are going to evaluate our limits analytically, which means analyzing the equations and drawing conclusions without looking at the graph. Now in our warm-up, we have an equation of a parabola. We can tell that because of the x squared, and we want to go ahead and graph this function. Now my guess is that you probably do not remember how to graph a parabola when it's not in vertex form. The first thing that we need to do is find the coordinates for the vertex. The x-coordinate is found by doing opposite b over 2a, and the a, b, and c values are the lead coefficients for our quadratic. So I can find my x value to be 4 divided by 2 times 2, or 1. So this tells me now that my vertex has an x value of 1, and if I plug in 1, I can find that the corresponding y value is going to be negative 1. Now when I go ahead and graph this function, its vertex is at 1, negative 1. Because my a value is positive, I know that it's going to be facing up. Now we talked yesterday that we can either graph our parabola by using t-charts or by using patterns. I'm going to graph this using patterns. So my function, because the a value is 2, is going to go up 2 over 1, then up 6 over 1. And I know that my graph is symmetrical, so it will do the same thing on both sides. Now the problem that we're going to run into is that depending upon the x value we are asked to evaluate, we may not have our graph that extends that far. For example, in the first problem we're given, part A, we're asked to evaluate the limit as x approaches 0. Now recall the other day we talked about how when you are looking at your graph, you want to have the graph as it approaches from the left and from the right. So as I approach from the left, that looks like this. From the right looks like this. And I can see, I can see as I approach from the left and from the right, in both scenarios, I can see that I am approaching this point right here. And this point is at 0, 1. So as my x values approach 0, my y value approaches 1. And for that reason, I would say that the limit as x approaches 0 is equal to 1. Now that wasn't too difficult, but it was kind of annoying if we're being honest. If I look at my next problem, now I want to know what happens as x approaches negative 3. And my graph doesn't go that far. Not at all. The rate of increase for my y values, my graph definitely would not include these values. However, what we want to recognize is that for my parabola, because of the kind of equation that it is, I know that this graph is continuous. I know that it is a u without gaps. So any x value that I might choose to pick on my parabola, if I were to pick any value from the left and from the right, would approach the same point. It would approach the same point that happens to be on my parabola. So what I see is that in order to evaluate the limit as x approaches negative 3 in part B, all I have to do is plug negative 3 into my equation. Alright, so let's go ahead and see how that's going to look. I'm going to do 2 times negative 3 squared minus 4 times negative 3 plus 1. And the end result is that we have 18 plus 12 plus 1, which gives us 31. And my graph definitely would not have gone up that far. The same technique would be very helpful for part C, where we're asked to find the limit as x approaches 4. So now, rather than trying to mess around with my graph, I can simply go ahead and I can plug in 4 for my x value. So I'll have 2 times 4 squared minus 4 times 4 plus 1. And the end result gives me 17. The next question that we want to ask ourselves is, do we always have to graph the function, or when can we avoid graphing the function and simply plug in an x value? Pause the video and talk about this for a moment with your partner. Okay, so hopefully the result that you came up with is that we don't always have to draw a graph. For many limit problems, you don't have to graph at all. And that's part of the reason we analyzed so many graphs the other day. If you recognize that the function you are being asked to graph is continuous at this point, and it exists at this point, then to find the limit, all you have to do is plug in the function value. And that's what this says right here. This part up here in the purple says, if the curve has a y value at the given x value, so basically that means if there is a point there, and it's continuous, so that means that there's no breaks or gaps in the graph. And we will get into a much more in-depth definition of continuous later in the unit, but for right now this just means that it continues without any breaks. So if that happens, if the function's defined, if there's no breaks in the graph at that point, then to find the limit as x approaches that a value, we don't have to graph. All we have to do is plug a into the function. Now we've got to be careful because sometimes the function is undefined at the given x value. And when this happens, we have to do some work. By work, I mean simplify, reduce, rationalize, etc., so that we can get a new equation which allows us to plug in x. What we're going to do now is take a look at a couple more examples where we can find the limit analytically without having to draw a graph. We could draw a graph, however, graphing is time consuming, and when you don't need to, that can be quite helpful. Consider this first problem. It appears to be a rational function. However, we learned the other day that whenever we have rational functions, we always want to first try to factor and reduce. If we go ahead and factor this problem, we'll see that we get x minus 1 over x minus 1. And the factor x minus 1 can cancel off. Now we learned the other day that when a factor cancels, instead of having a vertical asymptote, we have a point of discontinuity. So this graph has a point of discontinuity at the x value of 1. Now to find the actual ordered pair for this point of discontinuity, we take a look at the reduced function. So the reduced function will be equal to x minus 1. And visually, we know that the graph x minus 1 is a line with a y-intercept of -1 and a slope of 1. So this graph would go up 1 over 1, up 1 over 1, up 1 over 1, and it would continue in this fashion. However, we have a point of discontinuity when x is 1. Now, based on the graph that I just started to trace out, we can see that this point of discontinuity occurs at 1, 0. Now, we don't have to have this graph to draw our conclusions about the limit, but it definitely helps us have a bigger picture. Now, we learned the other day that a limit is the value that the function approaches, the value that it approaches from the left and from the right. And as we look at this, as we approach 1 from the left, we are approaching a y value of 0. As we approach from the right, we approach a y value of 0. So even though I am not allowed to directly plug in 1 into my original function because it is undefined, I can still find my limit. And my limit is equal to 0. So because the limit as x approaches 1 from the left for f of x is equal to the limit as x approaches 1 from the right of f of x, then that means that the limit exists, and the limit as x approaches 1 for f of x will equal 0. In this next graph, we are asked to evaluate the limit as x approaches 5 for our tangent graph. Now we do know that our tangent graph has points of discontinuity. So what we need to figure out is if our tangent graph is continuous for the x value we are asking about. So when x is equal to 5, what we are trying to evaluate is the tangent of 5 pi fourths. And if we think about our graph and our tangent function, we know that tangent of 5 pi fourths has a value. At 5 pi fourths, tangent is equal to 1. Since this function is defined at this value, then to find the limit as x approaches 5, all we have to do is directly plug in 5, and we can find out that this limit is equal to 1. Pause the video and discuss any questions with your neighbor. This next function here is our constant function, the limit of 8. This is a horizontal line. Whenever we are dealing with constant functions, the limit as x approaches any x value is always equal to the value. So the limit as x approaches any number of a constant function is equal to that constant value. Because the function is never changing, it is always equal to that constant. So in part B, the limit of 8 as x approaches -4 is still going to be equal to 8. Now for our next function, we have the limit of the natural log of cosine of x as x approaches 0. Now there's a couple of things that we have to consider here. First of all, cosine of x is always defined, so I know that I can plug 0 in here for x. ln, however, is not always defined. And again, this goes back to those graphs that I referred to yesterday to help us have an easier time graphing these functions. Whenever we're dealing with a natural log or a log graph, this is our basic function. It has an anchor point at 1, 0. If we take a look at what's going on here, we know that the cosine function is always defined. We know that our natural log function is always defined as long as the input is greater than 0. So let's take a look at what's happening here. In order to evaluate the limit, we are going to try doing a direct substitution. We're going to try plugging in 0 for x. Now if we evaluate this, we'll have the natural log of the cosine of 0. And we know that the cosine of 0 is equal to 1. And based on the graph that we're looking at here, when x is 1, my natural log is equal to 0. Therefore, the limit as x approaches 0 of the natural log of cosine of x is going to equal 0. Now you may be looking at this problem thinking, how in the world am I supposed to remember that? Well, here's some stuff that you should remember. Any log, it doesn't matter what base, for any log, if you do the log of 1, it's going to equal 0. I don't care if it's a natural log, if it's a log base 7, log base 30, it does not matter. Whenever your input is 1, the answer is going to be equal to 0. Our next graph is a piecewise function. Yesterday, when we analyzed piecewise functions, we went ahead and graphed both sections, and we analyzed our graph from the left and from the right. Instead of having to graph our function, we are still going to analyze our limits from the left and the right. This restriction, x less than or equal to 2, can be used to analyze the limit as x approaches 2 from the left, because that piece would occur with all of the x values smaller than 2. This next section, x greater than 2, we are going to use to help answer the questions, the limit as x approaches 2 from the right of g of x. Now in my first question here, I'm asked to simply find the limit as x approaches 2 from the left. So since I'm approaching from the left, I'm going to use my top equation. I'm going to plug 2 in for x, and I will get -5 for my answer. Now in part B, I'm going to approach 2 from the right. I'm going to plug 2 into the second equation and have 2 minus 6, and here I get -4. Now right away when I look at these values, what that tells me is that as I'm approaching 2 from the left and from the right, these are not the same values. Since they are not the same values, that means that my overall limit does not exist. In order for my limit to exist, the limit from the left and the limit from the right have to be equal. So when I get to part C and I'm asked to evaluate the limit as x approaches 2, I would say that this limit does not exist. And it does not exist because the limit as x approaches 2 from the left of g of x is not equal to the limit as x approaches 2 from the right of g of x. Now when you're writing your reasonings and your statements, I know that it's really common to leave off the names of the functions. And we all catch ourselves doing it. However, we really need to keep the g of x, the f of x, etc. in there. It's kind of like when we were doing our trig stuff and everybody wanted to leave off the x's and the thetas. We need to keep them in there. They are part of the expressions. Take a minute and work on part D and consult the results with your neighbor. When we look at part D, what we notice is we are being asked to change x minus 6 to x minus 7. And after making that change, we can see that our left-hand limit equals -5 and our right-hand limit equals -5 as well. Since both of these limits are equal to -5 and they are the same, then that means the overall limit exists. Remember, for a limit to exist, the limit from the left and the limit from the right must be equal. Pause the video and talk with your neighbors before we consider our last example. In this last problem, we are told that if our limit exists as x approaches 3 for our function h of x, we want to find the a value. So let's think about what this means. In order for a limit to exist, we know that the limit from the left has to equal the limit from the right. Let's write that down. So if the limit as x approaches 3 of h of x exists, then the limit as x approaches 3 from the left of h of x is equal to the limit as x approaches 3 from the right of h of x. Now recall that when x is greater than 3, that is my limit from the right, and as x is less than or equal to 3, that is my limit from the left. So as I'm approaching the value of 3, I would plug 3 into both of those expressions and they would have to be equal. So that's what I'm going to do. I'm going to start by saying 4x minus a would have to equal -x squared plus ax plus 1 when x equals 3. So we're going to plug 3 in there. Now, when you're doing this, you want to be careful because the negative is in front of the x squared. And when my negative is in front of the x squared, that does not mean it's included in my exponent. So as I'm solving this, I'm going to have 12 minus a equals -9 plus 3a plus 1. And if I finish solving, I end up getting 20 equals 4a, therefore a has to equal 5. Alright, that's it. Homework is worksheet 2.